Okay, welcome. So what we're going to be going over today is a discussion of electric forces and electric fields. So I'll go ahead and share the notes. That's what I want. And then briefly, I just want to real quickly review what we were talking about when we in the previous lecture. So in the previous lecture, we discussed electric charge. And we kind of broke electric charge, the effects of electric charge down into static and moving charge. Now, the idea behind electric charge, it's a fundamental attribute of matter. And it is an attribute, and it's responsible for electrical and magnetic effects. Okay. So say electric and magnetic effects. Now, the magnetic effects primarily come from moving charge. We're going to be sticking to static charge in this lecture, and just in general, we're not really going to have time to go into much beyond circuits. There are always some magnetic considerations in circuits, but a lot of times you're more interested in really in the energy transfer that's going on with circuits and how you use the movement of electrical charges and electric charged particles, I should say, or charge carriers to carry energy. All right. So that's one of the big things that kind of goes on there. All right. So to get into this, we're gonna first talk about electric forces now. And again, these are largely going to be dealing with static situations. Now, what I mean by that is we know from our experience with forces that they cause accelerations. We're not in this context, we're really only going to be looking at the force. We're not really going to be looking at the acceleration. The reason is that once you start getting into the accelerations and changing the positions of objects, you end up changing the forces of objects. So again, this is not a constant force situation if we're really considering electrical forces. So you really need calculus to do a deep analysis of the motion that comes with the forces on electric charge. All right, so the main law we're going to use is Coulomb's law. And this will probably look familiar in form because in form it's very similar to it's quite similar to Newton's law of universal gravitation. So we'll compare those. But briefly, I just want to indicate what each of the symbols mean. So I'll do this F sub E. This will be electric force. For Coulomb's law, it does require two charged objects to exert a force on each other. So Q1 will be the charge of object 1. Q2 will be the charge of object 2. And then R will be the distance between the two objects. And all of these things are going to be relevant, or they're going to be described in a relationship that is Coulomb's law. Now, in order to do this, we are also going to need a constant that is called K. This is the Coulomb constant. Now, it's important to remember that this is not the charge that's in a fundamental unit of charge. This is a constant that relates quantities in Coulomb's law. Coulomb did a lot of work. Charles Coulomb did a lot of work in electrostatics, so there's a lot of things named after him in the field. So it's fortunate for him. But this is Coulomb's constant. And Coulomb's constant is equal to 8.99 times 10 to the ninth. And the units, we'll talk about the units, but first I'll give you Coulomb's law. We have the electric force, you have Coulomb's constant, and then you have the two charges multiplied together divided by the distance between the two. So the units of Coulomb's constant are newtons, because we want to end up having newtons on both sides, because that's what the units of force are. And then we're going to have 2 units of Coulomb, so Coulomb squared cancel in the denominator, because we on the right side, we have Coulomb squared in the numerator, and then we'll need 2 meters squared in the numerator. So that is what Coulomb's constant is. Now, as a reminder, Newton's law of universal gravitation was the gravitational constant G, m1, m2 over r squared. So you can basically see that it's quite similar. We have a different constant, of course, where G was equal to 6.67 times 10 to the negative 11th, and the units were Newton meter squared per kilogram squared for that constant. But the form is quite similar. We have a product of the attribute that causes the effect. So charge causes electrical effect, mass causes gravitational effect. We multiply those two together, divided by the square of the distance between the two. This is what we call an inverse square law. And both electric and gravitational forces ultimately follow inverse square laws. All right. Now, I do want to give you an indication of when Coulomb's law will be appropriate. And then I'll try to also indicate when it won't. So Coulomb's law will works for point charges and spherical charge distributions. Okay, now what I mean by a point charge, this is basically a situation where we're going to treat as if the charge or the charge object occupies a single point in space. Now that is never actually true. All objects have a certain shape, but a lot of times we can make that approximation. So when we're dealing with very small charged objects, be they electrons, protons, even charged cells or charged molecules, we'll typically treat them as point charges. That's just typically how that goes. When it comes to spherical charge distributions, this mostly comes in when you charge like a metal sphere. It turns out that the way if you look up an image of a Van de Graaff generator, that's just a solid metal sphere on an insulating platform. The way charges distribute over those surfaces are they kind of go to the very outer edge and they distribute equally. So that's basically, the charges are all like they're repelling each other. They want to get as far away from each other as they can. That's how they do it. Okay. Now it takes a little calculus to prove it, but it turns out you can prove that that's identical to using just a point charge centered at the center of the sphere. So in this case, your R in Coulomb's law, it's measured from the center of the sphere. And this was, we did this similarly when we were using Newton's law of universal gravitation on planets. Okay. So that is important to remember. Now, Coulomb's law in a certain way can be used to find other shapes, but it requires calculus. Okay, so we're not going to get into that. Basically, what you do is you'd kind of break a unique shape up into a bunch of a combination of a bunch of point charges, and then you do the math for all the point charges and you add them all together. And the way we ultimately do that technically is calculus, and we're not, that's beyond the scope of this. We're not going to get into that. So hopefully that makes sense. I do want to give an example. I like this example because one, it does help. It does allow us to calculate forces, but two, it also allows us to compare gravitational and electric forces. All right. So you may have heard this, maybe not, but you may have heard that gravity is a weak force and electricity is a strong force. And you might think, well, that doesn't really make much sense because I jump off a 30-foot cliff, I hit the ground. It doesn't feel like gravity is a weak force. Well, it turns out that, and this example is meant to show us that it turns out electrical forces are in fact significantly stronger than gravity on the scale of the charged object we deal with. Now, what's interesting about this is that it's the gravity tends to dominate on larger scales, and this is because on average, charge is balanced. So on larger scales, the electrical forces just kind of cancel out. but gravitational forces don't. So when you have large amounts of mass, they're always attractive. There's no repulsive gravity as far as we know. So that's why gravity tends to be much more relevant on the scale of like solar systems. But you get down into smaller areas and electrical forces have to be much larger. And this is the idea of this problem. Now we're going to need some information about different about protons and electrons. So the charge of the electron is equal to negative 1.60 times 10 to the negative 19th. The charge of the proton is actually equal to just the opposite of the charge of the electron. So that's 1.60 times 10 to the negative 19th. Put the units there, coulombs. The mass of the electron is equal to 9.11 times 10 to the negative 31 kilograms. And the mass of the proton is quite a bit larger. It is I think it's 2.6. I need to remember that. I used to know all this, used to have it all memorized. Yeah, 1.26 times 10 to the negative 27 kilograms. Okay. And then I'll write down our K constant, 8.99 times 10 to the 9th, and our G constant is 6.67 times 10 to the negative 11th. Units, getting those right. We've got everything in SI, so we're fine. I should probably write down the R as well. R is equal to 0.530 times 10 to the negative 10th meters. This is about half an angstrom, and it's roughly the scale of a hydrogen atom. Okay. So quite small. But when we find the electrical force, what we will do, and you may want to run through these calculations yourself just to see them. But when we find the electrical force, what we get is we end up with, one thing I wanted to talk about. I'm going to actually make a note of this before I do this. My suggestion. Where people will get thrown off is with the sign of these electric charges. Okay. So here's the thing. If we were doing a full calc-based physics class, this electric force equation would be a vector equation. But in order for that to work, you need to have spherical, you need to at least have spherical, or at least have polar, probably spherical vector coordinates, which we have not discussed. And going into this now, it's probably not worth the time it would take. So my suggestion when you're using this force equation, use Coulomb's law to find magnitude of force. To find magnitude of Fe. And what this means is it basically means that you ignore signs. Okay. And the only place signs come in is on the charges. The R is not gonna matter because it's squared. But the signs will come in on charges. But what those would do, those would specify the direction of the force along the vector between the two particles. And again, like I don't want to get too far into that, but if we just find the magnitude, we can find direction by using the idea that like charges repel and opposite charges attract. Okay. And that is actually a much simpler way of finding the direction if you're not diving into the entire, the more nuanced bit of mathematics with that. So, excuse me. That's what I suggest with that. So that's what I'm going to do. For this one, I would know that the direction was attractive. It doesn't ask anything about the direction. It just says to compare the force. So that's why I'm just going to do both of the charges as positive. So we'd have F sub E equals K. Actually, tell you what, K Q1 Q2 over R squared. So this would be 8.99 times 10 to the 9th times 1.60 times 10 to the negative 19th. And since we're dropping the sign, that just gets squared because these things have the same charge. And we divide this by 0.530 times 10 to the negative 10th. and then that thing is squared. And once you do this, plugging in, you should get something along the lines of 8.19 times 10 to the negative 8th newtons, okay? So that's a tiny force, but these are also fairly tiny objects, okay? And it turns out that this acceleration would be quite large, just from the electric force between these two. Now, there the fact that this electric force is so strong, it turns out that there is something that prevents these things from accelerating towards one another. That's a quantum mechanical effect, which again we're not going to get into. But the electric force, particularly given the size of these two particles, like you look at the masses are quite small. That force is going to produce a lot of acceleration, particularly on that electron. Okay. But even on the proton. So that's just something worth keeping in mind. Now, if we wanted to find the gravitational force, well, G M1 M2 over R squared. So this is going to be 6 point, and signs 6. Okay. Signs don't come into play here. There we go. 6.67 times 10 to the negative 11th. And then 9.11 times 10 to the negative, not 110, but 10 to the negative 31 times 1.26 times 10 to the negative 27. And you'll notice that in the numerator, like the denominator is going to be exactly the same. But you'll notice that in the numerator, the numbers are a lot smaller, okay? The constants are smaller. And then the exponents on the masses are, well, they're a lot more negative, okay? And again, the exponent on the constant is also negative here. So this is indicating that this is going to be quite a small force, and it turns out to be very small indeed. It's approximately equal to 2.72 times 10 to the negative 47th newtons. So when we compare these two magnitudes, the electric force is, a little less than 40 orders of magnitude higher than the gravitational force. And this is why we say gravity is a weak force compared to electricity. Because fundamentally, the gravity of the proton and the electron, they're not really affecting the behavior. Okay. We could argue that maybe they are a little bit, but again, they're affecting it on such a small scale that the electrical effects are far, far, far more important. Okay. So this is why we say gravity is a weak force. All right. So that was just it was an interesting little example to go through, given that. All right. Next thing I want to talk about, electric fields. Now, basically what electric fields are, and even other fields, I get to talk about gravitational fields, and you can adapt this to other different types of fields. But it's basically the electric effect of a charge where other charges, or I don't want to say, sometimes there are other charges there, but what this really is it's without reference to the charges affected by the field. Okay. So really what it's an attempt to do here, it's an attempt to quantify the effect would have on other charged particles if they were present. Now they may or may not be present, but the electric field, it's kind of an attempt to isolate the effect of a single charge that it would have on the universe around it. Now, it only has an effect if there are other charged objects nearby. So that's one thing, but the point is that the electric field is just an attempt to do that. Okay. And we will we will use field lines to visually represent a field. And I do want to give some rules for how field lines are drawn. The first rule is that field lines start at positive charges. Okay. Now, what do I mean by this? Well, basically what I mean is that if you have something, with a plus Q right there, basically your electric field, and I'll draw 8 field lines for this one, is going to radiate outward kind of like so. Okay. So this is what you're seeing with that electrical field. So the green is the electrical field. All right. And that's the idea, is that that they start at positive charges. The second rule is that field lines end at negative charges. So this is what we'd call an isolated charge, an isolated point charge at negative charges. And basically a negative charge is going to look similar, except the field lines are going to be pointing towards that charge instead of away from it. Okay. So we have negative Q, and now the field lines are pointed inward at that charge. Now, you might ask what happens if you have multiple charges. So I'll just do another diagram over here. If you've got a plus Q and a minus Q over here, one of the third rule I'll get at in just a minute is that field lines can't cross. But what you get is you get field lines pointing directly from the positive to the negative. Now they'll start to curve, and you'll even get field lines coming out of the top, but they will curve around and point into the bottom. Now that's kind of what it'll look like. Now that field setup is what we call a dipole. I'm not gonna go much further than that, other than to tell you that. But when you have something like that, that's basically what's going on. You have what's called an electric dipole there. Okay. So the third rule, and I basically just said this one, is field lines never cross. All right. So when you have a bunch of fields together, you're not going to get them to cross. So field lines never cross. The reason for this is that basically if you have if field lines were to cross, that would be like saying two different things should happen. Instead, what they'll do is they'll kind of curve so they don't have to cross. So you'll notice that basically that's kind of what happened up here at the dipole, is that if we were just had two single charges independently, then they'd kind of be radiating outward. But basically all these lines curved, all these field lines curved in order to kind of accommodate what was going on in both of the charges. And I think I actually drew 9 that time. Yeah, I think I drew 9. But anyway, the idea is that's kind of how things would go. The fourth one I'm going to tell you is that positive charges feel a force I'll be a little bit more explicit, in same direction as field lines. All right. And the idea here is, okay, if we have a plus Q right there, and we'll have another plus Q somewhere out there as like a point charge, we know that these are going to be repelling. So we can say from the get-go that we'll call it a test charge. That's going to feel a force in that direction. Now the other one will feel a force in the other direction, but we're not really concerned about that for now. Now what we have is this thing would be having field lines radiating outward like so. and better. And the point is that the field line at the point of the test charge is pointing to the right, and so is the electrical force. All right, but if I do like a negative test charge, say down here, so we have negative Q, well, this one is going to be attracted to that positive charge. So it will feel a charge in that direction. So the fifth rule is that negative charges feel a force in opposite direction as field lines. Okay. So that's the idea. Now you might be wondering, but won't, if there are two negative charges, won't they still be repelled? And that is true. So we'll go with negative Q, and then we'll just have the field lines are now pointing towards the object. Again, that was kind of our first rule, that field lines point towards this. Now, if I have a negative Q right there, well, we know this negative Q is going to feel a force. It's going to be repelled from the other negative charge. So it's going to feel a force in the opposite direction. Okay. So again, we can see that it's going in the opposite direction as the field line. All right. So that's what's going on with electric fields and electric field lines. All right. Now I want to give a simple formula for electric fields, a couple of them actually. And the first one is just kind of the way you can think about electric field. An electric field, and this definition may be more helpful when it comes to reminding yourself of these equations. It's the electric force per unit charge. Now, what this means is it means we can have our electric field, and again, that the symbol for electric field is a capital E. That's why we never really use that for energy. Energy is common enough to use in electrostatics and in electrodynamics that you don't really want to be using confusing symbols. So E is the symbol for electric field, so that's where that gets used up. That's why we never used it for energy. And the formula is then that E is the electric force on some charge divided by the charge, the magnitude of the charge. So Fe, this is just write that down, electric force on an object. And Q is the charge of the object. Okay. Now this can be rewritten as, and this is another common way you'll see it, is F sub E is just Q times the electric field. So again, that's saying the same thing. In order to find the electric force on an object, you need to know, one, the electric field it was in, and two, the charge of the object. All right. So that's something to keep in mind. All right. Now, the next way to think about this, or the next equation I wanted to talk about, the electric field of a point charge or a spherical charge can just be done with Coulomb's law. It's just slightly reformulating Coulomb's law such that it's a field, not a force. And again, we had the force was equal to the electric field divided by the charge. Well, in this case, we can just say that the electric field, you're still gonna have the K, but this time you're only gonna have one of the charges because again, we're removing the second charge. We just want to know the electric effect of that first charge. And again, you're going to take the magnitude of that charge, multiply it by Coulomb's constant, and divide it by R squared. Okay. So that is the electric field of a point charge. Now, one other thing I wanted to talk about that I think might be relevant here is the electric fields of capacitors. Now, I wanted to bring this up because many of you have worked with capacitors in your circuits class. So basically what a capacitor is, we'll do positive charges in red, I guess. You have a bunch of positive charges on one plate and a bunch of negative charges on the other plate. And the idea is that you have, we can know this. That's just kind of how capacitors work. How that gets there is going to be more of a topic for circuits. But given that we got a bunch of positive charge on the top, a bunch of negative charge on the bottom, we're going to have an electric field pointing from the top plate to the bottom plate. And while I'm not going to go through this here, it can be demonstrated with calculus that your E field is constant between capacitor plates. So it doesn't matter where you put this, you put a test charge in your capacitor, you have a constant E field between those two capacitor plates. Now, ultimately what this means, a capacitor, you may know this, is a method of storing energy in a circuit. And ultimately, this is the energy is stored in that electric field. Unlike a battery, where you're storing energy in the form of basically a chemical reaction that, when the connection is right, that chemical reaction can occur and send electric and generate electrical current. In the form in a capacitor, what you're doing is you're storing charge basically in the form of this or you're storing energy in the form of this electric field. And the whole idea is that what this electric field means, it means that it can do work on a charge to move a charge from the top plate to the bottom plate. And fundamentally, given that electric field could do work on a charged object, we'll say, that electric field could do work on a charged object, the idea is that means that there is potential energy in that electric field. And this is going to be one of the things we'll talk about in the next lecture, okay? Getting into electric potential energy and then ultimately electric potential. Now, one thing I wanted to do, I wanted to take a quick look at a couple of example problems. So this is going to be the end of the content. If you don't want to see the examples, you can end there. But here I will show you some of these example problems. And what we got here, this one says, basically it gives us a couple of charges, and then it says, okay, these two charges that are given. So in part A, it's this one and this one. Those are fixed in place. For part B, it's this one and this one. These are all fixed in place. Or no, sorry, that was that one. And it says, okay, they can be positive or negative. They have the same size, same magnitude. And we want to do the magnitude of an electric force on a test charge positive Q that is placed at P, okay? So basically what we're doing here is we're putting a plus Q right there. Now, basically the idea is that this point charge is going to have a force from each of these two embedded charges, okay? And the whole point that we want to know is okay, which one is going to be the biggest. Now, we have to do this qualitatively. We're not given the numbers to do it quantitatively, okay? You could make up some numbers if you were so inclined to do it that way. Like you give 1 to each of these charges, you could give, make each one of these blocks 1 and then calculate it that way. However, what I'm going to show you kind of how I would do it qualitatively. So I would draw arrows from the two forces. So this is a positive charge. It's going to be attracted to both of these negative charges, and they're an equal distance away. So they're both the same size. So that means the F net here is equal to 0. Okay. So if we have a plus Q right here, well, it's going to have a large attractive force towards the negative Q, but it's also going to get repelled by this guy. However, that one will be smaller, and it'll be smaller because it's further away. Okay, so basically what we have is we have an F net to the right, and it is, it's somewhat smaller than a square that I drew right there. Okay. Now for this one. So we have a plus Q. Well, this one is going to have an attractive charge to the left from the negative, and it's also going to have a repulsive charge from the positive to the left. So, or sorry, this one should have been left. I don't know why I said right. So this one is also to the left, but its F net is large. Okay, it's twice as large as these forces we've been dealing with so far. Okay. Now here, what we're going to have is we're going to have two repulsive charges, and one of them is going to be the full block. That's basically the length of the force I've been giving for a charge that's one square away. But for this one, the force from the second positive charge will actually be reduced because it's further. So this one will be a bit smaller. So our F net here is a bit smaller than for C's, and it's in the opposite direction, but we don't care about direction. We're only asked for magnitude. Okay, so first of all, one of these has a 0 magnitude. That would be A. Now for B, the forces, they partially cancel out, but they don't totally cancel out. So that's why we have a small F net to the left. Now for C and D, both of the forces are additive, but in C, both of the charges are having the same effect, whereas in D, one of the charges is having a reduced effect. Okay, and that's just due to distance away. So D is actually going to end up with a smaller force than C. So that is how you would look at that one. Okay, so hopefully that makes sense. All right. I'll just real quickly do an example problem here. This one says calculate the strength and direction of the electric field E due to a point charge of 2 nanocoulombs at a distance of 5 millimeters from the charge. Okay, so this one indicate right here, the point charge, that indicates Coulomb's law. All right, so that is what we're going to do. So in this case, the electric force E, electric field, not electric force. It's just going to be KQ over R. Now we do need to get the units right. So I'll write K down first, 8.99 times 10 to the 9th. And then coulombs, see if you get the units right on this one. It's 2.00 times 10 to the negative 9th, or sorry, Q. That is in coulombs. You don't want to use C as your charge, because even though we do it for volts, where we use V for volts and V for voltage, for C, that symbol C means capacitance, so that's one of the reasons we use Q for charge. And then R is going to be 0.005 meters. That's converting millimeters to meters. So there you go. And then you just plug these in. You get 8.99 times 10 to the 9th. And then 2 times 10 to the negative 9th. All over 0.005. And I'm not gonna run through that, but that's basically how you do it. If they then wanted you to find the force on a charge, you just take the electric field you'd found and multiply by a charge. Okay, so that is basically what's going on with this one. And hopefully that makes sense in terms of finding electric fields, electric forces, things like that. Hopefully a couple of these examples make sense. Please let me know if you've got any other questions. But with that, I'm going to go ahead and end the recording there.